Okay, let's say we have a cyclic device. It's a heat engine extracting heat from some high temperature reservoir and rejecting heat to a low temperature reservoir. This thing operates in a cycle, so it produces work W cycle. So let's analyze this cycle using the energy balance and the entropy balance and see what we get. So how about the E balance? So let's apply the E balance to our cyclic heat engine. So I'm going to write the energy balance and I'm going to apply it over the cycle. So I'm going to write here Q over the cycle minus the work produced over the cycle is equal to delta E over the cycle. Delta E over the cycle. Now, over a cycle, there are no changes in any properties. So the change in energy over the cycle is 0. That goes away. So what that says is that the work produced by the cyclic device, is equal to the heat added over the cycle. This is a net heat or total heat added over the cycle. Now, heat is brought in and then rejected. So Q cycle is actually Q high, which is being added to the system, minus QL, which is being rejected by the system. So W cycle is equal to QH minus QL. So W cycle is equal to the heat over the cycle, which is equal to Q high minus Q low, or Q in minus Q out. If you want to put an in and an out here instead of a high or a low, that's fine with me. That's fine with me. Okay? What about the entropy balance? So let's put a little box around this. What about the entropy balance? S balance. Okay? Now, first of all, I'm going to write the differential form of the closed system entropy balance. So remember, we have ds is equal to del Q over T interaction plus del S gen. Now, for our cycle analysis stuff, our air standard cycle analysis, one of the assumptions is internally reversible. There's no irreversible processes going on in here. So that means there's no entropy being generated. So I'm going to put a 0 here. So I'm going to write internally reversible. Internally reversible. Okay? No entropy generation inside my heat engine. Now, one consequence of that is, so let me draw a picture of the piston cylinder device containing my working fluid. So here's my working fluid right here. So here's my gas. Now, let's say somewhere inside the system, the temperatures were different. Let's say we have a temperature over here, I don't know, T, and then over here I have T plus a delta T. So it's cool over here and warm over here. So cold and warm. What's going to happen to heat transfer inside my gas, where I have a cold side and a warm side? Well, heat is going to get transferred from hot to cold. In fact, that's heat transfer across a finite temperature difference, delta T. I can't have that. Why? Because inside the system, there's no irreversibilities. So what that means is the temperature inside of my gas cannot vary spatially. There can't be a cold part and a warm part. It all has to be the same temperature inside, or I get heat transferred across a finite temperature difference inside my system. That means that the interaction temperature, or the temperature that I measure anywhere on the surface of my system, anywhere, the interaction temperature where the heat crosses the system boundary has to be equal to the gas temperature. There has to be a uniform temperature, spatially uniform. Temperature is the same everywhere inside my gas. So this temperature is not an interaction temperature, it's just the plain old temperature of my gas, T, okay? So no delta T inside. This implies temp is a uniform T. Temperature within my air, my gas, my working fluid is uniform everywhere. It's at a temperature T. T is the temperature of the gas. So I get ds is equal to del Q over T. Okay? Now I'm going to solve that for the heat transfer. Multiply both sides by temperature T, flip the equation, and I get del Q, I'll do it down here, and I get del Q is equal to T ds. Okay, internally reversible, that's what I have to have. That's what I have to have. Now let's integrate this over the cycle. Let's integrate this over the cycle. The heat transfer integrated over the cycle is my Q cycle. Q cycle, which by the way is equal to my work. Work cycle, okay? So what this means is work of the cycle is equal to Q of the cycle, which is equal to the integral over the cycle of temperature ds. Put a box around that. The cycle work for our internally reversible piston cylinder device closed system, the cycle work is equal to the integral of TDS. What does that mean? That means if I plot my cycle on the temperature entropy plot, TS, here's my cycle. There's my cycle. Just a circle, let's say. The area bound by the TS curve. The area bound by the TS curve is the heat added over the cycle, which is the work produced over the cycle. So this area in here represents my cycle work. W cycle. That's nice because remember the area bound by the PV curve was the boundary work. Remember the area bound by the PV curve was the boundary work or the cycle work because the work is boundary work. So we have similar interpretations of the area bound by the PV curve and the TS curve for our cycle analysis assumptions. The area bound by the TS curve is the work over the cycle, or the net heat transfer or cycle heat transfer Q high minus Q low. Okay? Now, before we move on, I want to point out one more thing about the entropy balance. Not only can I calculate the cycle work, by getting the area bound by the TS curve for the cycle, I can get the heat addition and the heat rejection too. So let me write this here. So recall, del Q is equal to TdS. That means the heat transfer over some process, 1 to 2, is equal to the integral of the heat transfer over the process 1 to 2, plus the integral, which is equal to the integral of TdS over the process. So not only can I get the net work produced by the cycle from the TS diagram, but I can get the heat transfer. Let me show you what I mean. TS. State 1, here's the path. State 2, this area, the area underneath the TS curve. The area underneath the TS curve is my heat transfer 1 to 2. Okay? This area, which is the integral of TdS, is equal to the heat transfer from 1 to 2. Okay? So the TS diagram, unlike the PV diagram, not only just shows you the work, but it shows you various heat transfers. Let's do an example here and I'll show you how this works. Let's do a little example and I'll show you how this works. Let's do a little example. Let's say I have 2 cycles. Here's one, and here is the second cycle. These are both TS diagrams. So let's say, here's my first cycle. There's my first cycle, okay? So the cycle's going in this direction. There's my first cycle. And here's my second cycle. Lower on the TS diagram. Lower on the TS diagram. Let's compare the works over the cycle. So this is cycle A, and this is cycle B. Well, the work is represented, the cycle work is represented by the area bound by the TS curve. So this equals work cycle for cycle A, and this equals the cycle work for cycle B. Notice these triangles are approximately the same shape. They are the same shape. So I have the cycle work for cycle A equals the cycle work for cycle B. Okay? Same shape and size. Okay? Same area bound by the TS curve over the cycle. Same works. Let's compare the heat transfer into the system over the cycle. So let's compare QH. Let's see here, what's QH for cycle A? Where's the heat being added Where's the heat being added in my cycle? Well, notice that entropy is increasing. Entropy is increasing on the upper portion of the cycle. So entropy goes up on the upper portion of the cycle. And if entropy goes up, so S is going up, that means Q is being added. And we know that Q is being added from the hot place into my working fluid. So Q high A is actually equal to Q in. Okay, so heat is being added in this part. Q in is being added in this portion of the cycle. Now, as we can see over here, the area underneath the TS curve represents the heat transfer for an internally reversible process. The area underneath the TS curve represents the heat transfer into the system. So this blue area is my heat transfer into my system. So this blue area represents my Q in, or my Q high, if you like, for cycle A. Okay, because entropy is increasing from this point to this point. Everywhere else, from here to here and from here to here, it's declining. So the heat rejection is the area underneath the bottom part of the cycle. Heat addition occurs at the top. Okay, so I got a pretty big area. How about this one? The heat addition, Q in B. If you like, that's Q low B. That's represented by this area. So the heat is being added on the top portion of the cycle. The cycle is going in the clockwise direction. So that's where the heat is being added, okay? So Q in is represented by that area. Which cycle has a greater heat input? This part, the cycle A. So note, Q in A is greater than Q in B. Areas different. And what areas am I referring to? I'm referring to the crosshatch areas, okay? Okay, let's calculate the efficiency. Let's compare the efficiency. So remember, efficiency for a heat engine is the work over the cycle divided by the heat input from the high temperature place. Now in our case, the works are the same, but the heat transfers are different. Cycle A has a greater heat transfer than cycle B. So the denominator is larger for cycle A than cycle B. So that means the efficiency of cycle A is less than the efficiency of cycle B. And that's because the heat transfer is greater into the system for cycle A than cycle B, okay? So this is kind of cute. This means I can envision all sorts of cycles. All I got to do is draw them, and I can basically eyeball the heat transfer, the work, the efficiency. I can pull everything of interest off of the TS diagram. I can get the heat rejection too. I can not only get the heat, I can get the heat transfer in, but I can get the heat transfer out. I can do that too if I want, but usually we're interested only in the heat transfer in. So unlike the PV diagram, which only allows us to calculate boundary work, we can get all sorts of information off the TS diagram. the works over the cycle, which is the area bound by the TS curve over the cycle. But I can also get the heat input. And the heat input corresponds to those sections of the cycle, those processes, where delta S is positive, where entropy is increasing. Okay? This is quite nice. Okay, let's do a numerical example here.